Example 12.3 gives us a function f given by the equation f of x equals negative x squared plus 6x. If we take a look at one of our previous examples, that would be example 12.1b, we already have the vertex form for this done. The vertex form of this equation would be f of x equals negative 1 times x minus 3 squared plus 9. So from there, we should be able to identify three things about this particular function. Number one, you should be able to tell me the exact location of the vertex. The vertex will be located at 3, 9. And the second thing we should be able to say is whether or not the parabola opens up or down. So here, the a value is negative 1. That would tell me that this parabola is going to open down. And then third thing that we can say is whether or not there's a stretch or a shrink. Now, when we talked about transformations in section 4, we always talked about looking at the absolute value of a. And the absolute value of a is just going to be 1. And the criteria says that if it's greater than 1, then we're going to have a stretch. If it's less than 1, then we're going to have a shrink. So in this case, since it's exactly equal to 1, we would say that there is no stretch or shrink. We are not going to have either of those happening. And that becomes really helpful for part A. Part A says graph f on a Cartesian coordinate plane. And I'll also notice that the domain for this function is supposed to be all real numbers. So I'm going to come up here to the point at 3, 9. And since there is no stretch or shrink, I should be using the basic shape that I get from the squaring parent function. If you need to go back and look at your parent function library to help remind you of that shape, certainly do so. And we will have that particular shape. Let me go over 2, down 1, 2, 3, 4. So I'm always going to the vertex and then going out from there. And this gives me a pretty good idea of what this parabola is going to look like. But as I look further down the list of things that I'm going to have to do, I'm going to have to state the domain and range. So for part A, we've got the domain, which was given to us. That's just going to be all real numbers. The range is not given to us, but we can find that from the graph. Since this is opening down, it's going to be heading in the negative direction, unbounded. So we would start at negative infinity, and then the highest value that we would go to is positive 9. So negative infinity to positive 9. And then for part B, we're looking at the, that was part B. Part C, rather. Part C is going to take us into the intercepts. Now, there's a way to formally calculate the intercepts, but if we can actually find them nicely on the graph, then we can use that as our means of being able to get to the intercepts without having to go through the algebraic analytic way. So the pattern is, from the vertex, if you go over 1, you go down 1. If you go over 2, you go down 4. If you go over 3, 3 squared would be 9, so we would have to go down 9. And if you go out 4, 4 squared would be 16. That'd take us all the way down here to negative 7. So there are some other points on here. Since our window is large enough and our vertex is starting way up here at the top of the window, we can actually make this parabola the biggest that we've ever made. And we also have talked about the axis of symmetry being that vertical line that crosses right through the vertex. And so because of that axis of symmetry, I know that there's another point on the x-axis at the origin, and then there's another point over here at -1, -7. And so I can complete the parabola like this. And I really don't need these other helper lines here. Let me see if I can erase those. There we go. So that is the graph of f. And more importantly, I can see I cross through the origin, which counts as an x-intercept and a y-intercept, and I also cross through the x-axis here at 6. So for part C, we're just being asked to state the intercepts, and I would certainly say x-intercepts would be at 0, 0, as well as 6, 0, and the y-intercept is going to be redundant. It's going to be 0, 0. So the x and y-intercept end up being the same for 1. Part D takes us to stating the relative extrema. There is one point on here that counts as a relative maximum, and that would be the vertex. Vertex is a very important point. So we do have a relative maximum located at 3, 9. In terms of relative minimum, I would say there is none. Part E, state the intervals of increasing and decreasing. Everything to the left of the axis of symmetry, or the left of the vertex, is increasing, because you always have to read from left to right. And then everything to the right of the vertex, or the axis of symmetry, is going to have a decreasing behavior. So let's write that out. We are increasing from -infinity to +3, and we are decreasing from 3 to infinity. And then finally, we want to write the equation for the axis of symmetry of our graph. The axis of symmetry we've already marked, and it is that vertical dashed line that's red. It is located with all the x values being 3. So we just simply write x equals 3. So again, this is another example where we were able to get the graph done, and we were able to allow the graph to drive the analysis part. The analysis part was all of the B through F stuff. And there are times when it'll be more useful to do the analysis first and then use that as a means to get the graph completed. So we need to be fluent in how to do both of these.